Section: Introduction. We've been exploring how to make large language models, LLMs, better at tasks like talking to users or answering questions. To do this, these models first go through a training phase where they learn from examples of how to follow instructions. This process usually starts with supervised fine-tuning, SFT, where the model is trained on a set of examples that show it how to respond to instructions. After that, it might go through another round of training with reinforcement learning, where it gets feedback on its responses to help it learn the best way to reply. This feedback can come from humans or be generated automatically. A big question in our field is whether we can get good results just from the SFT part, which would be great because collecting feedback for reinforcement learning can be costly. We've been working on this by creating and using a dataset called Alpaca, which has 52,000 examples of instructions and responses. We used it to train a model called Llama 2-7B, and we got it to perform as well as a model that isn't openly available, called Text DaVinci 003. Then, we made a subset of Alpaca called AlpaGasus, which has 9,000 of the best examples according to another model, GPT 3.5 Turbo. This helped improve the model's ability to follow instructions. We also looked at another dataset called Llama, which has 1,000 carefully chosen examples and found it did even better than AlpaGasus. This made us think that maybe the quality of the examples is really important for training. In our work, we revisited the idea of making datasets for training models to follow instructions. We noticed that longer examples might be helpful, especially since other research showed that models trained with reinforcement learning tend to produce longer responses. So, we tried a simple idea. We picked the 1,000 longest examples from Alpaca and trained our model on them. Surprisingly, this approach worked really well, even better than using AlpaGasus or Llama. We also found that by just making the responses from these long examples better and adding some variety to the training process, we could create a model that was among the top performers. We didn't stop there. We wanted to understand why our approach was so effective. We did several tests and found that our model wasn't just making longer responses. It was actually giving better answers. We also checked if our model was still good at using facts correctly, and it was, even when compared to other models trained on different datasets. Finally, we tested our method with different datasets and models, and in various competitions, to see if it worked well in general. And it did. To sum up, we found a surprisingly effective way to train language models to follow instructions better by just using the longest examples from a big dataset. This method is not only simple but also doesn't require a lot of resources, making it a strong option for anyone looking to improve how models understand and respond to instructions. In related work, others have shown that training models to follow instructions is crucial for them to interact effectively with users. There's been a lot of effort to create diverse and high-quality datasets for this purpose. Some have used advanced models to generate examples, while others have focused on carefully selecting the best examples with the help of humans. There's also been discussion about whether instruction tuning mainly helps models mimic a certain style or if it also improves their ability to handle a wide range of tasks. Our work adds to this conversation by showing that focusing on the length of examples can be a simple yet powerful strategy for instruction tuning. Section Summary. The section introduces the concept of aligning pre-trained large language models, LLMs, for tasks like user interaction and question answering through supervised fine-tuning and reinforcement learning. The authors present Alpaca, a dataset of instruction response pairs, and demonstrate that fine-tuning on a small subset of high-quality instructions can outperform larger datasets and even models fine-tuned with millions of preference data points. They also discuss the importance of diversity in demonstrations and the effectiveness of selecting the longest responses as a simple and inexpensive heuristic for curating high-quality instruction following datasets. Section: Fine-tuning on long instructions is a very strong baseline. We began by exploring how the length of training examples impacts instruction following training, IFT, and discovered that using longer examples can be a simple yet effective way to create small, high-quality IFT datasets. This approach often performs better than more complex methods. When looking at existing methods, recent studies have shown that training large language models, LLMs, on a small, carefully chosen set of instructions can significantly improve their ability to follow instructions and complete tasks. For example, using GPT 3.5 Turbo, we evaluated instruction sets on a scale from 1 to 5. We then selected the highest-rated examples to create a dataset called outperforms, based on 9,000 instructions. Additionally, we gathered 750 top instruction response pairs from online forums and wrote 250 examples ourselves to increase the variety and quality of tasks, forming the Llama 1K dataset. These datasets aim to make LLMs more useful in conversations. Our approach was to focus on the length of responses. We chose the 1,000 longest responses from two large datasets, Alpaca 52K and Eval Instruct 70K, to create our own IFT datasets. This decision was based on the idea that longer responses tend to be more informative and challenging for LLMs to generate, which could help the models learn better. Interestingly, we found that the longest responses didn't always align with the highest-rated ones by LLMs. For instance, many of the longest responses from Alpaca were rated lower than those in the outperforms dataset. To test our method, we compared our datasets of the 1,000 longest examples against the full original datasets and others curated based on high scores or manual selection. We used Llama 2 to 7B models for this test and evaluated their performance on 5 different datasets. Our models trained on the longest examples performed better than those trained on other datasets, including those manually curated, which suggests that selecting training examples based on length can be very effective. We also looked into whether the preference for longer responses by models like GPT-4 could have influenced our results. However, even when using a different model, PALM2, as a judge, our approach still showed a preference. Lastly, we examined the role of response length more closely. While our training examples were longer, this wasn't the sole reason our models performed better. For instance, the training examples in Llama 1K were much longer than ours, but the performance was similar. This indicates that while response length is a factor, it's not the only reason our models were preferred over others like Llama 1K. Section Summary. Fine-tuning on longer instructions proves to be a strong baseline, as demonstrated by the study's findings. The research shows that selecting the longest responses for instruction following training datasets consistently outperforms more complex methods, leading to improved performance across various evaluation datasets. This approach is particularly effective, even outperforming carefully curated datasets, and the advantage is consistent even when using different judges for evaluation. Section. How far can we go with 1,000 instructions? We've discovered that choosing instructions based on their length is a good starting point for instruction following tuning, IFT, but even then, our language models, LLMs, don't perform as well as those that have been fine-tuned with more complex instruction sets or through methods like reinforcement learning with human feedback, RLHF. So, we're curious about how far we can push the performance of LLMs by fine-tuning them with just 1,000 instructions. To do this, we first made the instructions more suitable for IFT by refining their style. Then, we combined our dataset with Neftune, a new algorithm that enhances IFT by adding noise to the data, and found it to be effective. We also checked if our models could follow instructions well without their performance dropping in other areas, like factual knowledge, even when we forced them to give longer or shorter responses. To refine the instructions, we focused on improving their style, structure, and detail level because IFT's goal is to teach LLMs how to interact with users, not necessarily to provide them with new knowledge. We suspected that more detailed instructions could help models understand and generate more complex and logical responses. We didn't just pick the longest instructions assuming they were the best. Instead, we used an advanced LLM to review and improve them. This process, inspired by the chain of thought method, involved having the model critique an original response and then generate a new one based on both the critique and the original instruction response pair. This led to a refined dataset we call refined alpaca -1K longest. For evaluating how well models followed instructions, we compared models fine-tuned on our refined dataset against those trained on other datasets, including a baseline set of 1,000 instructions and others. We used the Alpaca Eval 2.0 benchmark, which compares models based on their win rate against responses judged by GPT-4 Turbo. Our refined instructions showed a clear advantage, significantly outperforming the baseline in various model architectures. For example, models trained with our refined instructions had a win rate of 59.9% across different architectures, much higher than the 20.2% win rate of the strongest existing method at the time. Moreover, when we combined our refined dataset with Neftune, we saw even better performance, achieving a win rate of 7.88% in one of the model architectures, which was among the top performances on the leaderboard. This demonstrates that a simple set of 1,000 well-chosen and refined instructions can compete with more complex and expensive training methods involving hundreds of thousands of examples and reinforcement learning. Interestingly, we found that making the models generate longer responses didn't necessarily improve their performance on the benchmark. Even when we increased the maximum response length, the improvement in win rate was minimal or even slightly negative. This suggests that the quality of instruction following doesn't solely depend on the length of the responses. In summary, by refining a set of 1,000 instructions and using a novel algorithm, we were able to significantly improve the performance of LLMs in following instructions, demonstrating that careful selection and refinement of training data can yield competitive results even with relatively simple and cost-effective methods. Section Summary. The section explores the potential of using 1,000 instructions for instruction following tasks, IFT, with language models. It discusses refining the style of the longest 1,000 instructions to improve the quality of responses and evaluates the performance of models fine-tuned on these instructions. The results show that even with a simple dataset of 1,000 instructions, competitive performance can be achieved, and increasing the response length does not significantly impact the model's performance on the benchmark. Section: Evaluation on Factual Knowledge Benchmarks. We looked into how models trained on smaller sets of instructions perform on tasks that aren't just about following instructions, using a large language model, LLM, to judge their performance. We focused on a part of the Open LLM benchmark, which tests various skills of an LLM like understanding common sense, handling multiple tasks, and being truthful, but we left out two datasets because one had overlap with our training data and the other was too challenging for all models. When we fine-tuned models using the Llama 2-7B as a starting point and tested them on data from Alpaca and Llama 1K, we found that on average, making the models learn from Alpaca 52K slightly improved their performance. However, models trained with a specific set of 1,000 detailed instructions from Alpaca and Llama did even better, especially the ones that used refined instructions, showing improvements of about 1%. The best results came from models that used these refined instructions, with or without an additional fine-tuning step called Neftune, achieving around 56.4% and 56.5% success rates, respectively. This suggests that the quality of the instructions and how they guide the model to understand and complete tasks can significantly impact performance. We also explored why training models with longer, detailed responses work so well. We found that simply making the model's responses longer didn't necessarily improve their quality. Even when we made sure the models produced longer answers, our specially trained model still outperformed the others, indicating that quality matters more than quantity. Interestingly, as we continued to fine-tune one of our models, its responses got shorter over time, but its performance improved, suggesting it was getting better at focusing on what's important. We provided examples of how our fine-tuned model could generate more natural and detailed responses compared to others. We also noted that our approach consistently did better than other methods that tried to improve upon the basic Alpaca dataset. In discussing the quality of instruction following tasks, IFT, we argued that simply choosing longer instructions doesn't automatically lead to better models. For instance, even though the Llama dataset's instructions were longer, this didn't always translate to higher quality, as seen in the lower evaluations from one of the LLM judges. This highlights that other factors must be considered to enhance the effectiveness of IFT datasets. We also touched on how fine-tuning LLMs with specific datasets, like responses from ChatGPT, can make them mimic ChatGPT's style closely, as rated by humans and LLM judges. However, this approach didn't always improve the model's performance on natural language processing benchmarks. In contrast, our work shows that carefully chosen instruction datasets can lead to models that are both preferred by LLM judges and perform better on tasks. In conclusion, we've demonstrated that selecting instructions based on the length of the replies can be a simple yet effective way to prepare datasets for aligning LLMs through supervised fine-tuning. This method, which is both cost-effective and straightforward, competes well against more complex alignment strategies. Our findings challenge the current understanding of what makes an IFT dataset high quality and how it affects model performance. We also highlighted the importance of considering safety and ethical issues when using LLMs, although we didn't delve into specific strategies for addressing these concerns in this work. Section Summary. The section discusses evaluating models trained on small instruction datasets for tasks beyond instruction following, using the Open LLM benchmark. It highlights the impact of instruction length on model performance, suggesting that longer and more detailed instructions may positively influence the model's performance on various tasks. Additionally, the section emphasizes the effectiveness of using reply length as a heuristic for pre-selecting instructions for LLM alignment, challenging the current understanding of high-quality instruction following datasets and their impact on fine-tuned model performance in standard NLP benchmarks. Section Impact Statement. In our paper, we aim to push forward the area of machine learning. We acknowledge that our work could have various effects on society, but we don't believe there are any specific outcomes that need to be emphasized in this section. We would like to express our gratitude as M.A. received support from the Google Fellowship and the Open Phil AI Fellowship.